Hello students, welcome to the series of lectures on linear integrated circuits and applications. So in this video I am going to explain the self-learning topic of sine wave generator as a Wien bridge oscillator. Okay, so in the previous video we have already seen the RC phase shift oscillator. Okay, so the way how we have calculated the frequency of oscillation that can be required and what is an amplifier gain that we already see in the previous video. Okay, it's similar to that. Now let us look into the analysis part of Wien bridge oscillator. Okay, so let's get started. Let me take the pen. All right. So these are the three important learning outcomes of today's lecture. The first one is you'll be able to understand the principle of operation of sine wave generator, and the second one is you'll be able to analyze the operation of the Wien bridge oscillator, and the third one, let us solve some problems which are related to the Wien bridge oscillator. Okay. So this is the pin diagram of IC741. In every video I am putting the pin configuration of IC741. So please go through this each and every pin of IC741. Alright. So this brief introduction which is related to the oscillator, that also we have already completed in the previous video. Okay, the most important point you need to remember from this slide is that the sine wave is one of the most fundamental waveform, and the generation of sine wave is a challenging task because we are going to be seeing that ideal characteristics of a sine wave. Okay, so this is a general configuration of an oscillator circuit. This also we clearly seen in the previous video. So this triangular symbol, whatever that is there, which is an amplifier section, and this is the feedback section. Okay, so this we already seen, and this is the positive feedback, and this is the transfer function. So let me write transfer function is equals to V naught by Vs equal to A by 1 minus A beta. So this A is nothing but the amplifier gain, this beta nothing but the feedback gain, please remember, and the feedback gain beta is equals to Vf by V naught. So where here this V naught is nothing but output of amplifier section. Not only it is output of amplifier section, but also it acts as a input to the feedback. Okay, so that you need to remember. Okay, so when we take the denominator of the transfer function is equated to 0, then we are able to see the two important conditions. That is, magnitude of loop gain is equals to 1, and the phase angle around the loop is equals to 0 degrees or 360 degrees. So once you identify from the circuit whether it is satisfying these two conditions, that is Barkhasen criteria condition we can call, then you can say that the circuit whatever that you are designing, which is acting like an oscillator. That can be possible if and only if it satisfies the two important conditions, that is loop gain equal to 1 and the phase angle around the loop gain is equals to 0 degrees or 360 degrees. Alright, so this also we have seen in the previous video. So in order to analyze the circuit, okay, so to analyze we are going to be following the important steps that to be followed. The first important step is that we need to calculate the value of beta. I clearly mentioned the beta is nothing but the feedback gain. Okay, so which is given by the ratio of Vf and V naught. Okay, which is a complex number. And after calculating the value of beta, now we are putting our effort to calculate amplifier gain. A is equals to V naught by Vf, which is a pretty straightforward. And once you calculate the value of A and beta, we are taking the multiplication of those gains will be equated to 1. Now we are comparing the real part and the imaginary part, and taking the imaginary part in one side and then taking the real part in one side. Now we are able to calculating what is the frequency of oscillation that can be required for Wien bridge oscillator, and similarly for the amplified gain also we are calculating. Okay, all right. So this is our discussion of today's video lecture. So this is a circuit diagram of Wien bridge oscillator, and you can clearly identify from this circuit is that this is a feedback arrangement. So the feedback arrangement we have given to the non-inverting input of operation amplifier. So this is an amplifier gain. So this is a beta. This is V naught, and here I can write this is Vf. Okay, So I can also establish a relation between beta, that is output by input. So this V naught becomes input to the beta network and Vf is the output of the beta. So this beta is equals to Vf by V naught, where A is equals to V naught by Vf. So as this is a non-inverting operational amplifier, so the amplifier gain is equals to 1 plus Rf by R1. Please remember this formula. Okay. So if the operational amplifier is ideal, straight away we are taking the formula as 1 plus Rf by R1 if that is a non-inverting operational amplifier. Okay. Just recall whatever that we have already discussed in the previous lecture, that is a RC phase shift oscillator. In the RC phase shift oscillator, that is an inverting operational amplifier. Okay. So remember, there the non-inverting input terminal is directly connected to ground. So therefore we have taken or we have applied the feedback arrangement to the inverting. So therefore that is an arrangement of the inverting. Okay. Now let us see whether it is producing phase angle around the lobe is equals to 0 or 360. As the name itself indicates, which is a non-inverting operational amplifier. Okay. Non-inverting means the output waveform is in phase with respect to the input waveform. So therefore obviously the phase angle around the loop is equals to 0 degrees or 360 degrees. So which is satisfying one of the Barkhausen criteria. Okay. So obviously we can conclude that. So this is a circuit which is capable of producing the sustained frequency of oscillations. Okay. Sine wave generator that can be possible with this circuit. Now let us see the analysis part. Okay. So to see the analysis part, what I have done is that I am taking the feedback arrangement separately for you to understand better. This is a frequency selection network I can call. Okay. So this is the V naught and this is the input we are going to be applying to this feedback network. Okay. And see the arrangement how that is looking like. So this is the series combination. I am putting this as a Z1 and this is the parallel combination. I am putting this is Z2. Okay. Now only two impedances which are acting and we are taking output across this Z2. Okay. Using voltage divider rule. Okay. So using voltage divider rule, let me write here. Using voltage divider rule, so the beta is nothing but V naught by Vi, which is Z2 by Z1 plus Z2, where Z2 is nothing but what? The parallel combination of R2 and XC2. Okay, that we have already written here. Okay, and what is Z1? Which is a series combination of R1 and C1. Okay, and when you multiply here, when you take the same thing here in this, you will be getting like this. Okay, once you check yourself, beta you'll be getting something like this. Okay. Now in continuation to this, we can also rewritten the beta as something like this. Okay, and for Barkhausen criteria, the imaginary part is equals to 0. Okay, the moment when you consider the statement like this, and whatever the imaginary part that we can easily identify from this beta. So let me call this as equation 1. From equation 1, this is an imaginary part. Okay, so you take the imaginary part and equate it to 0 and you will be getting the frequency, that is omega equal to 1 upon under root of R1 R2 C1 C2. Okay, or in other words I can also write in terms of frequency of oscillations, F naught is equals to 1 upon 2 pi under root of R1 C1 R2 C2. Okay, I can also write like this. Okay, so this is in terms of hertz. The units for frequency is hertz. Okay, so this we can easily identify. If you take R1, R2 equal to equal resistance value and C1 and C2 equal to same capacitor, and that will be modifies like this. This is F naught is equals to 1 upon 2 pi into RC. So this is the frequency of oscillation. It can be possible if and only if you take this condition. Okay, if you take this condition, then we are able to see the formula for the frequency of oscillation if not equal to 1 upon 2 pi RC. And recall whatever that we already derived for the frequency of oscillation in the case of RC phase shift oscillator, that is F naught equal to 1 upon 2 pi RC under root 6. But here F naught equal to straight away 1 upon 2 pi into RC. Okay, so this is the beta again we are able to calculating the amplifier now. Okay, so by setting omega is equals to 1 by r, so the same thing whatever I have written in the previous slide. So the imaginary part equal to 0 and beta is equals to 1 by 3. Okay, you can substitute the same thing. Okay, you substitute this in the previous equation, you will be getting beta equal to 1 by 3. You check whether you are getting or not. Okay, so due to Barkhasan criteria, we know that the loop gain is equals to 1. Okay, so where A is nothing but the gain of the amplifier. The gain is straight away we have seen that, which is a non-inverting amplifier. Now we know that this is the 1 plus Rf by R1. So obviously as beta equal to 1 upon 3, A is equals to 3. So this can be equated to 1 plus Rf by R1. Now this is the condition we have got from this. This is also very important condition we need to follow. Okay, so to get the frequency of oscillation, sustained oscillation if you want to get, this is the condition we need to follow, we need to take. Okay, so always you take the feedback resistance is at least twice of the input resistance R1, then only we are going to be getting the frequency of oscillation, or the sustained frequency of oscillation we'll be getting. Okay, so this is F0. Okay, so this is the analysis part of the Wien Bridge oscillator, which is pretty simple for us when we compare to the RC phase shift oscillator. The analysis is also very simple. So this is the designing of Wien Bridge oscillator. This you need to design with according to the data whatever I have given. Okay, you check yourself. Thank you students. Thank you for watching this video.